Hi, okay, this is my video number 18, right? um, I'll still talk on the stability of the linear system for the non-autonomous system, all right, which means we consider the system of the form that x, right? So where x is unknown and the matrix A depend on T, and also given that if the solution of that system, so let's call this system 1, okay, if the solution of that system satisfying, let's say x, let me write this thing, if the solution of 1, okay, satisfying x t naught equal to x naught, and they are defined for t greater than t naught, then the solution is given as x, yeah, then x t naught x naught with phi t x naught, yeah, where phi t we call it as a fundamental matrix. Phi t is a fundamental matrix. Yeah, fundamental matrix means it satisfy phi t naught. This is an identity. Okay, I have given the definition in the previous video, which involved the magnitude of the matrix A, yeah, or non-norm of the matrix A, and also some related theorem, which that if the solution of that system, yeah, system 1, the linear system 1, stable if and only if it is bounded. Okay. I have given that. So if the solution is stable, okay, solution stable, so we have theorem, solution stable if and only if it is bounded. Okay, I just recall what I have given in the previous video, because I'm going to continue this video with all those things, and as well as if the characteristic polynomial of that system stable, yeah, then every solution is asymptotically stable. So we also have the result that if the characteristic polynomial, if the characteristic polynomial of A in one stable is stable, then every solution of x dot ax is asymptotically stable. Okay. Now for those system, yeah, for x dot equal to atx, which is equation 1, if I can split the matrix A into the constant and matrix that involve T, so we have a kind of A plus C Ct, where A is a constant, where A is a constant metric, and CT is a matrix with each element depend on T, yeah? C, I, J, T, continuous. Yeah? We need this continuous. Then we have, or we can write equation 1. Then we can write equation 1, x dot as a plus CT x. Okay, so what we might expect that if the characteristic polynomial of A is stable, yeah, if the characteristic polynomial of A is stable, then we might expect that under a suitable condition on C, then the solution of that system also stable. So let's call this system system 2. Okay, so we are looking for what condition on C that make this system, the solution of that system, stable, provided that the if the characteristic polynomial of the matrix A is stable. So we have the theorem. I just state this theorem without proof here. Just state the theorem without proof. If the characteristic polynomial of A, if the characteristic polynomial of A is stable, the matrix CT is continuous, on T infinity, and we need this condition that the norm of CT is integrable, yeah? Then all solution of 2 is asymptotically stable. All solution of 2 are asymptotically stable. Okay, so this is a quite important result in order to determine the stability of non-homogeneous system. And this is non-homogeneous system because depend on T, and it is a linear system, yeah. Then we impose the condition on C that C continuous and integrable, then the solution of those systems are asymptotically stable. And the consequences of this theorem that if the solution of the characteristic polynomial of A is stable, CT is continuous, and the norm of C sufficiently small, yeah, the norm of matrix C is sufficiently small, then the solution are stable, yeah? And then the solution are stable. So we have those consequences of that theorem. Now let's see example on these things. Let's consider first example. Let's consider if you have x double dot plus x equal to 0. So this is a simple system. So if we let x dot equal to y. So obviously those equation becomes y dot is equal to negative x, right? Yeah, negative x. So if you look at the matrix of that system, matrix A, our matrix A is 0, 1, minus 1, 0. Yeah. And of course, if you find the eigenvalue of this, the eigenvalue is given as plus minus I, where the solution is of the form cos t and sin t. So we know that the solution is cos t and sin t are bounded, and the solution is bounded. So therefore, the solution for that system is stable. Okay, this is bounded. So therefore, the solution is stable. Now, if you look at I give you another example. So you consider x double dot minus 2x dot over t plus t naught plus x equal to 0. Yeah, if you convert into a system, then we let x equal to y, then we have those system becomes y dot equal to what? So we have negative x plus 2 over t plus t naught y. Okay, so obviously from this, if you write the matrix A, or our corresponding matrix A is this is 0, 1, minus 1, and 2 over t minus t naught. Okay, so of course this A I can write in terms of constant matrix and matrix with t. Sorry, so this I can write as a 0, 1, minus 1, 0, plus we have 0, 0, 0, 2 over t plus t naught. Okay, for the system without C, we have done in the first example, which is we know that stable. Okay, and then what happen if we have the equation where the corresponding system have that the stable for the autonomous part and plus the involved t. What happened to that kind of system? Okay, so let's try to look at this. So the fundamental solution of that system, and the fundamental solution of that, the fundamental solution is given as sine minus t plus t naught cos t and cos plus t plus t naught sin t. Yeah. And we know that as t goes to infinity, yeah, as t goes to infinity, so what happened to this solution? So as t goes to infinity, those t goes to infinity, so the first and second solution goes to infinity. So it means that all the solution are unbounded. So which means we have all the solution are unbounded, which means the solution is unstable. The solution for that system is unstable. Okay. Now, if you look at the the norm of C, yeah, the norm of C, look at the norm of C. I have defined what norm is. I have defined norm. So norm, we define norm as norm is a summation of each element of matrix C, yeah, Ij. So if you consider the norm of C, this is our C, is given by 2 over T plus T naught. So obviously for T big enough, as T bigger and bigger, so this is less than T over 2 over T naught for T is positive. Okay, if we choose T small enough, yeah, T small enough, what will happen? What will happen? That part getting bigger. So it means that it shows that in our case we have the even though the C is small enough, but this is not enough to show that the solution is bounded, because we have shown here the solution is unbounded. Yeah, the solution is unbounded. So it is not enough to show, if we have norm small enough, it is not enough to ensure the solution are bounded. Okay, so if we do the according to our theorem, we need to evaluate the integral of that norm. We need to show that in order to show the solution bounded, we need to show this integrable or we have some value in it. So if you evaluate this, we have Ts, this is ln T plus T naught over T naught squared, and of course this goes to infinity as T goes to infinity. So the solution is unbounded. Okay, so I have done on the linear system. For the non-homogeneous system, I gave you an example. Okay, so I stop here. Then in the next video I'll talk on the non-linear system. Alright, so I stop here. Thank you.